Welcome everyone. So to today's lecture, we will be walking across what are sequence-to-sequence models, how they work, what was the growth journey of sequence-to-sequence models to today's transformers, what were those limitations, how these evolved, and then we will get into a hands-on lab. To sequence-to-sequence models are composed of encoders and decoder. Encoder process input into a hidden representation, and decoder generates the output sequence step by step. We can see a visual representation of a sequence-to-sequence model. So here we have a advanced transformer, which is the latest and the most advanced version of sequence-to-sequence model. It is composed of encoders and decoder. In the encoder part, we have three layers: input embedding, which breaks text into token and then tokens into vectors, and positional data is also encoded into it. Multi-head self-attention model weighs the importance of all other words to understand context for each word. And the feed-forward network is a simple neural network that processes the attention output for each position independently. The decoder has mass self-attention, encoder decoder attention, and the final output generation attends to in the first layer, it attends to previously rendered word in output, preventing it from cheating by seeing the future ones. In encoder decoder attention layer, it feeds from the feed forward network of the encoder and finds the relevant input, and the final output is generated in the third layer. The example of or use case utility of sequence to sequence model lies in translation, summarizations, speech to audio, speech to text, or text to audio. Types of sequence to sequence models are RNNs, LSTMs, GRUs, and transformer. RNNs is what we spoke about earlier. These are simple recurrent connections. These are good for short sentences, but they struggle with long dependencies, and their utility lies in basic text generation. LSTMs are the advanced version of RNN, which had memory gates and cells. With this, they were able to handle the long-term dependencies, but they became more complex and slower. Similarly, GRUs were the simplified version of LSTMs with fewer gates. They were faster, less resource heavy, but slightly expressive. The example is chatbot and speech recognition. Transformer is something which changed the game. They completely removed the recurrence part of it, and they focused on the self attention mechanism. Along with that, parallel self attention, which could run in parallel, and it really fastened and improved the experience of how the use cases of translation text generation were done. So their strength lies in capturing global dependencies parallelization, but they require large data and they're compute heavy. Practical applications, we have already spoken about sequence to sequence model in terms of machine translation, text summarization, speech recognition, chatbots. We have spoken in terms of the different sequence to sequence model types, but let's summarize. So RNNs are the foundational but limited. LSTM and GRUs solve the memory issues. Uh, and transformers dominated modern NLP due to their attention mechanism. Attention allows model to focus on relevant part of input, improving accuracy. Let's look at the basic sequence to sequence model here. We have input sequence, output sequence. Beauty lies in terms of input is not dependent upon the output in terms of fixed length. We have stated earlier, RNNs were the early approach of sequence to sequence model with encoder and decoder. Encoder reads the input and decoder gives the output. And now let's deep dive into RNN, LSTMs, and GRUs and understand what was the vanishing and the exploding gradient problem. So as we have stated earlier, RNNs are composed of hidden state. There is a recurrent connection and output layer. The utility of RNN lies in terms of simple text generations, but they struggle at long-term memory use cases due to the vanishing and exploding gradient problem. And due to these problems, LSTM and GRUs are introduced as improvements. So long short-term memory solve the memory issue of RNNs by capturing long-term dependencies using information flow with gates. But the issue lied with LSTM was that they were taking too much time to train, and they were not able to fully utilize the parallel structure of GPUs. Gated recurring units try to simplify this with the help of fewer gates, but somehow they were also not able to fully capture the parallel abilities of the GPUs. And this is where the revolution happened with the help of transformers. But before we get into that, let's talk about the vanishing gradient. This occurs when gradient becomes extremely small during the backpropagation, preventing earlier layers from learning. Similarly, So the I mean the problem which lies here is in terms of no learning, and the long term contexts are forgotten. Similarly, for the exploding gradient, the gradient during the back propagation becomes exponentially large, which destabilizes the training, and the loss function diverges in this case. The problem causes the training to become unstable, and the fix lies in gradient clipping and careful initialization. The practical fixes for gradient problem lies in gradient clipping and proper initialization for the exploding problems, and batch normalization, and alternative activations like ReLU and leaky ReLU for the vanishing gradient risk. So to wrap up, vanishing gradient and exploding gradient are the fundamental training challenges in the deep neural networks. LSTM and GRUs were introduced to take care of this. And the key takeaway lies that they allow network to remember what matters, forget what doesn't, enabling breakthrough in NLP, speech, and sequential data tasks. Now let's look into self-attention. This is where the revolution happened. So self-attention is by which each word understands its weightage with by correlating with all other words. The computational formula for the self attention lies in the query key and value. So each word understand what it is looking for, what it contains, and what it will provide. And based on this input vector, these weights are calculated and the scores are given. At the same time, this attention self attention mechanism happens in a multi-headed way. So if we look at this input token, it divides a word into multi-heads, and then they try to run in parallel, understand different contexts in terms of semantics, grammar, correlations, and other things, and then they concatenate, and then with a linear layer multi-headed output is provided, which makes the models quite faster, and it provides in terms of real tangible effects and impact in terms of how accurate and real time results are generated. So with this, transformer family gave rise to three sort of architectures, which were encoder only or auto encoding models, which are like BERT for understanding, and autoregressive or decoder only models for generation, that is GPT, and encoder decoder sequence to sequence models for like T5 for transduction or summarization. So if you look into the summary of the sequence to sequence model, uh, before 2017 we had RNNs, then came the LSTMs, then came the GRUs, but the revolution happened in 2017 when the attention is all you need white paper was released, and this is where the single pre-trained model would fine tune for numerous downstream tasks, and it gave rise to the large language model. In 2018, BERT was introduced, and 2019 GPT-2 was there, which was able to generate a lot reliable and real-time text, and then GPT-3, and the rest is history. Now let's look into the hands-on of the sequence-to-sequence models. So we are using here the different libraries to in order for us to initialize. We are using PyTorch, as well as we have NLTK. Once it is run, we have the seed setup, and we know, okay, what device we are using currently. Once that is done, we are going into the loading of the movie data set from the NLTK. We are initializing an empty list, and then we are iterating over the categories in the data set, positive or negative, and we are converting them into numbers, that is 1 for positive and 0 for negative, and then it is being saved into the docs. So we have total 2000, and it is showing us the some of the samples. Then we are going to the next step, which is the pre-processing step. We are making lowercase characters. We are keeping only alphanumeric reviews, even if one character is there, and then we are trimming the long sequences. So with this first one, we clean the tokens and make them lowercase, and we keep all tokens that contain at least one alphanumeric character. Similarly, in the build vocab, we are building a vocabulary word to index mapping from the dataset. The our arguments are a list of tokens and labels. Maximum vocabulary size is also defined as 20,000, and minimum frequency is defined as 2. Similarly, we are numeralizing the tokens to integer ID using the vocabulary story, and then truncating the sequence longer than a max length. Then we are going into text data set. Data list of numericalized token is being generated along with the labels. If you look at the steps for the next one, so embedding layer, before we go to the step one, we have converting IDs into diverse vectors, and then RNN, LSTM, GRU layers are being created. Then hidden stages, states storage, allow later visualization of how the model evolves. Fully connected layer maps hidden state to class, log its binary classification here, and then last time step out used as a summary representation of the sequence for classification. So we have dimensions of word embeddings as 128, hidden dimensions are 128 for RNN, LSTM, and GRU, and the number, as mentioned earlier, we have only positive and negative sentiment. So when we run the RNN, we are passing these hyperparameters. We are initializing the embeddings, we are initializing the RNN layers, and then it's being run. And the forward layer, we have outputs. Hidden states are defined here, and then we are we are using the last time hidden for the state for classification. Same thing goes on for the LSTM classifier. We have the embedding layer, we have the LSTM layer, and then we have the fully connected layer. And then for forwarding, we have self embed, it's being called here. Output with the other parameters calls this, and then we are returning the output for this. Same thing goes for the GRU. So when we look at the capture multi-head attention, this is for the transformer part here. So transformer simple encoder with attention weight capture. This section defines a simplified transformer encoder architecture for the text classification and wrapper around the multi-head attention to capture attention weights, and the custom encoder layer with self attention plus feed forward network. So multi-head here, what we try to show is that we show okay how the multi-headed attention really works. We have the init where we are uh, declaring the multi-head attention layer, right? And then we are performing the self attention queries, keys, values by declaring all this, right? And then simple transformer encoder layer, if you look at it, we have this attention layer, and then we have linear dropout and linear 2, and here is a code for this. We are calling the relu function, the activation function. We have the forward layer using this, and then we have the transformer classifier, which is classifying using our embeddings, and we have the forward layer. So if we summarize this, we capture the multi-head refs, PyTorch, and multi-headed and save the attention weights for visualization. Simple transformer encoder layer, one encoder blocks with self-attention feed-forward network, residual connection, and the layer normalization. Here we show the training part of it as to how each epoch runs, what and how the iterations are done. And similarly, here these are invoked. If you see here, for RNN, we are just for all of these, we have two epochs. So for the first one, for the RNN, we have a training loss of 71, accuracy of 48, and then validation loss was that is equals to 70 and accuracy is 51. Same thing goes for LSTM, GRUs, and transformer. So if we explain it step by step, we have train one epoch, set model to training mode, loops through the batches, computes loss, back propagates, update the weights, tracks total loss, and evaluate.